if you've ever been swimming, then you probably realize that as you swim to the bottom of a pool, you can feel the increased pressure on your ears and your nose. That increased pressure is due to the weight of the fluid that is above you. Now, we can actually derive an equation that gives the pressure as a function of depth in a fluid. So we're going to look at the variation of pressure with depth. So here I have a giant swimming pool. There's the blue water. And I'm going to look at, imagine I have a cylinder-shaped bag of water floating in the water. Now, that's critical that it's the same material. It's not a hollow bag of air, because that would want to float. It's not a solid rock, because that would want to sink. It's made of the exact same material as the fluid around it. It's just in the shape of a cylinder. So, this cylinder, this green cylinder shown here, has some top area A, has the same area below. Height H is the height of the cylinder. So this cylinder has some weight downward, right? It's made of water, therefore it has weight. That can't be the only force acting on that cylinder of water. If it was, the cylinder would quickly sink. What else is acting on this cylinder of water? Well, it experiences pressure from being in a fluid, right? There's pressure pushing down on the top, there's pressure pushing in on the sides, and there's pressure pushing up from the bottom. But we know that the water should float in that cylinder, so the net forces acting on that cylinder of water have to add up to 0. If they don't add up to 0, it's going to accelerate. I mean, if this were a bag of air and I let it go, it'd accelerate up. If this were a giant rock in water and I let it go, it would accelerate downward. But because it's a bag of water in water, it stays put. So a couple other equations. So the volume of this cylinder, if we know the surface area A of one side, we can multiply that surface area by the length of the cylinder, its height H, and that gives us the volume of the cylinder. And then remember, the density of the material we're talking about is mass over volume. So, we're coming to those equations in just a bit. So, I'm going to look at the y forces. The x forces have to balance as well, but I'm not interested in the x forces so much because I want to know how pressure changes with depth, with y. So, let's look at the y forces. Well, there's a force, there's pressure on the bottom, and again, pressure is force per unit area, which means that there's a force on the bottom pushing up. There's a force on the top due to the water pressure pushing down, and then there's the weight of the cylinder of water itself also pushing down. Those all have to add up to 0. Well, I don't know what the forces are, but I'm interested in how the pressure changes. So I'm going to substitute in, right? We have pressure was force over area. So I can substitute that then. Force is pressure times area. So I'm going to substitute in here. So the pressure on the bottom times the area of the bottom of the cylinder minus the pressure from the top times the area of the top is equal to the weight of the cylinder, which is m times g, where m is the mass of the water in the cylinder. Well, I don't know what the mass is, but I have that relationship with density. So I'm going to solve this for m. M is equal to the density times the volume. I'm going to make that substitution here. Mass is density times volume. Here I have area. Here I have area. Here I have volume. So I want to break this volume up into, see if I can get an area out of it. But remember, we have this equation over here. So I'm going to pause the video here for a moment, and we'll continue from this point with the derivation. So continuing from where we left off, pressure on the bottom times the area, minus pressure on the top times the area, minus rho times the volume times g. Well, the volume of the cylinder is the area of the top of the cylinder times its height. So area times height. Note now that in this equation, every term has an area, and all the terms are equal to 0. So I can divide through by a. what happens is A's cancel on the left-hand side, and then 0 divided by A is still 0. So the A's effectively cancel. I rearrange this equation to bring this negative P top to the other side. I rearrange the equation, but I add rho GH to both sides. And I end up with the pressure at the bottom of the cylinder is equal to whatever the pressure is at the top of the cylinder plus the density of the fluid that the cylinder is sitting in, G, the acceleration due to gravity, and H, the height of that cylinder. Well, our cylinder was still kind of arbitrarily down in the water somewhere. So let's lift our cylinder up. So the top of the cylinder is at the top of the water. So if the top of the cylinder is at the top of the water, then H is just the depth below the water, right? H equals 0 is the surface of the pool. H of 1 meter is 1 meter below the water. H of 5 meters is 5 meters below the surface of the water. And the pressure at the top becomes the atmospheric pressure. So when you look at a swimming pool, what we're going to end up getting is there's going to be some water, or we'll look at a lake, there'll be some water. We now know H is the depth below the surface. How deep are you in the water? And the pressure at the top is the atmospheric pressure. P sub ATM for atmosphere. The pressure is not 0 at the top of the water because the water is sitting underneath an ocean of air, just like you and I are sitting under this ocean of air. The weight of the air above us is pushing down on us, causing pressure. There is on your skin right now, every square inch experiences 14 pounds of pressure. That's atmospheric pressure. So here it's not quite sea level here in Wisconsin, but if you're at sea level, typically the atmospheric pressure is about 14 pounds per square inch, or 101,000 pascals, or 101 kilopascals. Atmospheric pressure then is the air pressure at the water's surface. So we end up with this equation. The pressure at some depth h under the water, or under the fluid, is equal to whatever the atmospheric pressure is at the top of the fluid, plus the density of the fluid, times the acceleration due to gravity, times the height, or rather the depth, if you will, that you are under that fluid. So there are a couple of different ways of changing the pressure, right? As you swim down underwater, H gets bigger and bigger, causing the pressure to get bigger and bigger. That's what causes the additional pressure on your ears. Additionally, it depends on the density of the fluid. If you've ever been swimming in the oceans, or the Great Salt Lake in Utah, or the Dead Sea, you know that it's actually easier to float in salt water than it is to float in fresh water. Salt water has a higher density, so the pressure actually increases more dramatically as you descend. That actually helps you, we'll talk about this in a moment, helps buoyant force. It helps the force that holds you above the water. That helps you float. But here's the equation for pressure. Now your textbook, I believe, doesn't include this P atmosphere part. It just says the pressure is rho GH. That's not correct, right? Because you can't ignore the fact that there is pressure at the water's surface. So even if you're sitting at the surface of the water and H is 0, you don't experience any pressure from the fluid, from the water, but you do experience, you're still under Earth's atmosphere, you do still experience the pressure from the atmosphere that you're sitting in.